Good afternoon, everyone, and welcome to the HGIS session this afternoon. I hope everyone is having a interesting time at this year's Offshore Site Investigation Forum. We're actually one of the co-sponsors, and I hope you found the sessions informative. Today, myself, my name is Andre Haramugam. I am the general manager here at HGS, and I would like to take you through some details on our autonomous survey vehicle. Some of the things that I'll go through is an introduction to the company itself, why we decided to look at the ASV, the technical specs, the general concept, system and concepts, the functionalities that we looked for, the logistics of how we are to deploy it, our journey to date, some of the real-time testing we've done, the survey, equipment payload that we settled on, the real-world advantages that we looked at, some of the key differentiators that we spotted, a brief on our maiden project for the ASV, and also some of the things that we're looking forward to further on from now. So briefly, HGIS or Hurricane Geo Inspection Survey was formed in 2007. Those of you who are active in this region should be familiar with my outfit. Some of you may know us by just Hurricane. Essentially, we are operating now in Malaysia, Brunei, Myanmar, Thailand. We're also making some ventures into Vietnam. And from being solely focused in oil and gas, we have now branched out into renewables. We have a technology outfit which is called HGIS Robotics, looking at fronting innovations such as this ASV and drone technology, etc. We also have an investment arm looking at investing in geophysical and other equipment assets. So why the ASV? Basically, we covered various aspects, but some of the things that were pertinent and important to us was obviously the cost component, the accessibility it brings, the ability to operate in hazardous environments, the fact that is, at least in this region, a form of disruptive technology and creates a niche for the company, and the fact that we can employ the actual ASV as a force multiplier. In terms of cost, I think it's pretty straightforward. There's a reduction of manpower and personnel, there's a reduction of assets deployed, fuel consumption, so there's a direct correlation between the using of the ASV and also cost saving. In terms of accessibility, due to the small footprint of the ASV, it's very maneuverable and accessible to congested areas, anywhere with shallow water, because it only has a very limited draft, less than 1 meter, and anywhere where we deem it impractical for a larger survey vessel to come in. Another important point to note is the hazardous environments where sometimes we are exposed to. In normal circumstances, we would have to do small board operations and include onboard personnel, but in this case, using the ASV, we can avoid this. In terms of it being a disruptive technology, at least in this region, it's pretty much new. I am happy to report that we'll be doing our first maiden project in June, and it will probably be the first ASV job in this region, or if not one of the earliest employment of the ASV in this region. In terms of it being a force multiplier, we see that it can be simultaneously used on our conventional survey spread, so we can conduct essentially 2 surveys at the same time. So the general system concept revolves around having a small size vessel, usually equipped with a telemetry system, either through radio or Wi-Fi. It's then controlled by a shore-based operator, which can be onshore or can be on mother vessel, and in this particular instance, we focus on the autonomous concept. So the shore-based operator is basically capable of running the vessel, but more importantly, it's monitoring as the ASV is doing its autonomous work, ensuring the recording is there, the data quality is there, and other safety aspects. So for the technical specification, we looked at various avenues. One of the first is, of course, vessel control system. So we wanted it to have full autonomous capabilities, and also being able to remotely control. It needed to have the capability to do route and mission planning. It needed the capability to update all the sensor statuses and operational statuses, and also it needed to support electronic navigation charts. For the navigation system, this being basically a mini survey vessel, we needed DGPS systems, gyros, gyro compasses, an INS system, marine radar for collision, AIS, especially if you're operating offshore, and also electro and infrared camera, so that we get a view of what the ASV is actually seeing, and it can be used in limited visibility times, and also depth sounders. For payload integration, we went with what can be found on a survey vessel: a multi-beam echo sounder, geoswat, side scan sonars, sub-bottom profilers, motion centers, and also we look at the possibility of including a USBL head. For safety, obviously, the emergency start-stop component, stopping the propulsion, collision avoidance, and also a programmable system where, if at all we lost telemetry, it could on its own decide to go to a safe zone and maintain, standoff in that area until the operators can pick it up themselves. For communications, we looked at not only line of sight communication, but also SATCOM. So the capabilities include UHF radio, mesh radio network, and Wi-Fi. SATCOMs covers, Iridium, Inmarsat, and also VSAT system. We also insisted that it should support whatever QC needs our payload required in terms of real-time data transfer, and also the capability to support remote intervention from our onshore operators. The hull design, we wanted it to be able to operate in the high seas offshore and up to marginal sea stage. Launch and recovery, we wanted it to be able to be launched from small jetties or near beach shores, etc., etc. And also the footprint should be not too big for ease of deployment. Endurance, we wanted it to endure about a 24 hours endurance at 4 knots of average survey speed. This is an example of the GUI that's employed. On the right, you can see the different interfaces that we have and that we can track, and on the left is the actual bird's eye view of the survey and its plotted lines. So the platform itself is based on the M40. It's made of aluminium. The actual weight is about 400 kilograms and displaces about 450 kgs of water. The dimensions is as stated. Most importantly, you can see the draft is very shallow. It's 0.4 meters, and even with assets deployed, it only reaches a max of 0.8 meters. The power is electrical, so hence it's more stable and quiet. Communication distance is at a max of 5 kilometers. The max payload is 65 kilos. The average survey speed is between 4 to 6 knots. On a single charge, it endures for about 6 hours, but we also included a diesel genset in our design for continuous recharging of the battery itself. In terms of environmental endurance, it's designed for up to sea state 2 and with significant wave heights of about 1 meter or above. Functionalities, obviously, one of the most important thing is route and mission planning. That needed to be paramount so that it can do a lot of autonomous work. Distance control, basically, it's where we design the survey plot and ensure that the ASV never exits the extremities of the plot itself. Obstacle avoidance is very straightforward. In case of congested or heavy traffic areas, the ASV needed to recognize obstacles or collisions and avoid them as necessary. Battery calculation is with regards to endurance. For data communication, we went with a LTE setup, so the bandwidth is big enough to ensure all the data transfer happens quickly and everything can be communicated without any issue. Video monitoring, again, is in relation to the avoidance systems, and also it gives the onshore operators a view of what the ASV is actually heading up to. Remote control, this is basically for emergency issues where we can interject and take control of the ASV should we need to. And the autonomous capability is paramount. It has to do with the route planning, it has to do with the actual execution of the survey, etc. Logistics is pretty straightforward. Since it's a small footprint, we can transport overseas via shipping containers, and onshore or inshore, we can use trucks or pickup trucks and deploy it to wherever necessary. So our journey to date has taken us quite an interesting adventure, but we started off doing evaluation on all the technical aspect of different ASV providers and manufacturers. The selection of the ASV was based on proven track records, technical compliance, and also autonomous navigation needs, remote QC needs, and payload capability. And we use this basically to access its usage and its capability for inshore surveys, nearshore surveys, and offshore surveys. On top of that, we were looking for demonstrated proof of concept or trials, and also any recent actual project history. Some of the test parameters obviously involve plotting of survey lines and how the ASV would run it autonomously. It should be able to plot straight lines and then run at survey speeds of around 4 knots. Line changes were also very important, and the capability to do and plan line changes in congested areas. The approximate line change takes less than 30 seconds with an average speed of 4 knots, and in actuality, depending on the line spacing, it's much lower than that. As you can see below, is 3 meter spacing is about 10 seconds, 5 meter spacing is about 11 seconds, 10 meter spacing is about 14 seconds. Again, the vehicle itself is equipped with cameras, infrared and normal cameras for visibility during normal conditions and also low visibility conditions. Communication, again, is via Wi-Fi telemetry, so you can handle various weather conditions. This is the actual initial platform that we were exposed to. Of course, we have made modifications to it to suit our purposes. During the initial testing, when we visited the manufacturer, we did a straight line test. He was able to maintain course for quite a distance and also maintain an average survey speed of 4 knots. So real-time testing, it was done in the south of China. Survey area was around 600 meters times 1,000 meters. In total, there was 26 line kilometers done. The water depth ranged from 3.5 to 13 meters. Because this was at a testing phase, we used a spread that was provided by the manufacturers, which included a Teledyne Raison multi-beam sonar and also a Epronix Wavemaster. It took about 5 hours, and the environmental conditions saw yaw of about 0.8 meters in wavy water, and also we were facing about 1 to 2 meters squared speed, current speeds. This was the actual plotted lines that the autonomous system came up with. So in white, you can see what it has already acquired, and at this point is going on to acquire the cross lines in blue. These were the results from that test. from the multi-beam data. So for our particular purposes, we suited our needs, and we basically made sure the complement of equipment was what we wanted to and what we needed. And one of the things that we insisted on is everything should be modular. And why this was insisted on is because we knew that whatever equipment spread that was on board, we needed to ensure that at any point in time we could swap things out, or we could change things or change the spread as necessary, as requested by the client, or as needed by survey needs. But in generality, this complement that we see in this list right here is probably covers most of the operations. For positioning, we have Veripos GNSS, which is standard GPS, the GPS that we used. For navigation software, we included Kinsys. It's also pretty much our standard that we use for all our even conventional spreads. We have Dell computers set up for the top sites. The actual navigation software for the ASV itself was provided by November. For acquisition, we have a multi-beam and side-scan sonar system, HTEC 6205. And essentially, it's because it's a 2-in-1 system, can support multi-beam and single beam, so MBS and also triple S. Also included is Discovery bathymetric software running on, again, Dell top size, standard online software that we use. For the sub-bottom profilers, we are using a Inoma SES 2000. Essentially, it was recommended by our in-house geophysicists because of the it's good shallow water data interpretation, and it's very good anywhere up to 80 meters. It also has better resolution, and it's good to find, for example, buried pipelines in heavily sedimented areas. Besides that, we have other SES sub-bottom software, again running on Dell top sites, UPS for power backup, and also AVR to ensure that whatever equipment spread we put on top runs properly. Telemetry and Wi-Fi system was provided by the vendor. Some of the cross applications and capabilities we see is obviously for dredging and reclamation, for harbor work, for freshwater work in lakes, because it's easily deployed by pickup truck or lorries, for inland river work, estuaries, again for heavily congested zones, and coastal zones where we see there's a limitation on the draft of vessels that can go in. Some of the real world advantages that we like to point out is obviously, this system makes previously inaccessible areas accessible. So it's not only about congested areas, it's also about transition zones. It's also about, more hazardous environments, for example, swampy areas or areas where there are a lot of geohazards where we cannot risk taking in a larger vessel, and also areas where it's affected by a lot of tidal change, and at certain points the draft is too shallow for any conventional equipment or vessel to go in. Beyond that, close quarters in heavily congested areas offshore, for example, you see here a mobile offshore production unit, a jackup rig, and also an FPSO. And in under normal circumstances, this is it's considered dangerous operations because it's considered close pass. We have to design break-off points, and the closest survey line in this circumstance should be about 30 to 35 meters using a conventional marine vessel or survey vessel. But in the end, if you're using an ASV, you can bring the closest survey lines a lot more closer. The actual mother vessel can be on standoff outside of the exclusion zone, thus lowering the risk of maneuvering in close quarters as much as possible. Some of the key differentiators that we found or we understand right now is obviously the manpower needed for a conventional method to ASV system is vastly different. It's at least half the personnel requirements. In most cases, it's about a third. Vessel requirements is pretty straightforward. ASV is a small platform. simple to operate, whereas a marine vessel requires a full complement of crew, a lot of maintenance activities, sometimes intervention, technical stopovers and dry docks, and the ASB is pretty much avoids most of this thing. In terms of survey systems, because everything is modular and because it's designed to fit on a small footprint on the ASB, is much more, it's less complicated. Line change speed is very vastly different, simply because of the dimensions of a conventional survey vessel versus an ASB. And obviously the carbon footprint is way better. You're running a small diesel generator to charge batteries versus marine diesel engines as such on a normal survey vessel. Of course, in the whole process of trying to get our ASB up and running, we were also pitching various clients within the region, and I'm happy to report that we will be starting the ASB's maiden project sometime in June or Q2 this year. The details of the project is actually a river and channel survey. We're using a multi-beam, sub-bottom profiler, and side scan sonar. Should start, like I said, mid-June. The project location is in Brunei. The duration is about 60 days in total, but it's broken up into 2 campaigns. And the purpose is to conduct a biannual river survey utilizing the ASB to minimize nearshore personnel, avoid small boat operation, and any dangerous situation because it's a heavily trafficked area. This is an overview of the KB River itself. We have baseline data from previous surveys, so we will be looking to emulate or better the results from the surveys prior to this. So the survey is designed in 2 phases, and this is mainly because this will be its ASV's maiden job. By having 2 base stations, we ensure line of sight telemetry at all times. But eventually, the capability of the ASB should be able to do this in one longer campaign. And obviously, in this process or in this journey, we are looking always to the future. Innovation is a constant thing, and it's very important to us at HGIS. So these are some of the 3 things that we are continuously, or we have started to look into as we take receipt of our first ASB. One of it is to integrate all the topsides, the different topsides and computing power we have for the different sensors on board into one virtual machine, for example, a server, and then having that in a backup system. So we have a full backup and we minimize multiple topsides by doing this. We also would like to see how we can use or the possibility of using the ASV as a tracking vessel for our deep tow operations, for AUV and ROV operations. So we minimize a secondary multi-purpose support vessel specifically for tracking. Obviously, this has a lot of cost benefits to this. And also, we would like to develop the ASV as a touch monitoring system for shallow water pipe lay. And this is done by integrating a mini ROV that can be launched off the back of our ASV. So I thank you for joining us. That's what I have for you today. I covered a lot of the generalities. I understand that you may have many technical questions, so I've included the contact details of myself and my team. I look forward to your Q&A. Some of my technical guys will also be joining in, and we can hopefully answer all your queries. Thank you very much.